Hello my esteemed viewers. In this tutorial, the relationship among E, G and K will be clearly explained. The point of discussion here is very significant in strength of materials, as the relationship weds three altogether different measures of different properties of a material. First, the E, Young's modulus, which is a measure of the capability of linear deformations, capability of a material against linear deformation. The G, the rigidity modulus, as the name itself would imply, G is a measure of capability of materials against dislocations of dislocation of points in a component, a kind of angular deformation, which will bring in total deformity, total changes in the shape of a body, unlike the linear deformation. The third one, the K, the bulk modulus, as the measure of capability of materials against volume change. However, before we barge into development of the relationship among E, G and K, we need to understand what do we mean by complementary shear stress and diagonal tension and diagonal compression as a effect of this complementary shear stress. Consider a component which is subjected to forces this side and forces that side for some reason, because it has to serve such a physical condition in the real world, and we take a section somewhere over here. If we take a section and if you verify how exactly a small element, an infinitesimally small element, a cubical element will suffer from stresses, and we will just blow it up in the form of a figure like this, immediately there will be a shear stress developed on this particular surface. It's over here. In order to account for the equilibrium of this particular element with regard to horizontal forces or horizontal stresses, immediately a shear stress will be developed on the opposite face. However, it will be in equilibrium as far as sigma fx is concerned. However, it may tend to rotate with respect to center of this particular point. Therefore, in order to safeguard rotational equilibrium, a pair of shear stresses will be developed on the opposite faces, here and here. Now, this particular element is in equilibrium, safeguarding or satisfying the three fundamental equations of statics: sigma fx equal to 0, sigma fy equal to 0, sigma m, that is moment with respect to any point over the body, equal to 0. Therefore, it is in equilibrium, but it is still suffering from all round shear stress. This will develop first, and as a reaction this will develop in order to safeguard the two stresses on the opposite surface will develop exclusively to safeguard the rotational equilibrium. So developed stresses all around the surfaces, all around this elementary component, or a point within the stressed material, is called as complementary shear stress. These shear stresses, which will be developed in the form of reactions, will be complemented by these two stresses, which will again be considered as reactions on vertical faces of this particular element. Therefore, it can be said complementary shear stress will develop to safeguard the rotational equilibrium of an element. And we will just continue to establish what is the effect of this complementary shear stress and how it should be related with respect to linear stress. And the immediate effect of this complementary shear stress is the shape change. A cubical element or a cube, a square, will turn into rhombus. However, the moment of this point is over here. If this were to be A is here in A dash, and B is here, designated as B dash. So therefore the shear will always bring in total deformity, total shape change, okay, and dislocation of points. and here we just make it a little simple. A is here, has moved to A dash, B moved to B dash, and C and D is over here only because they are fixed. Let us assume that they are fixed. And this diagonal B dash D dash will get elongated and A dash C dash will get compressed. Therefore, this diagonal will be suffering from diagonal tension and this will be suffering from diagonal compression. One of the diagonals is elongated, other diagonal is compressed, and this is exclusively not due to axial forces. We have not applied any axial forces over this diagonal. It is a side effect that is caused by the shear. Shear is applied on the surface all around, but what it in effect, it makes one of the diagonals to get elongated, other diagonal get compressed. Therefore, the stresses that is developed in this diagonals are called as diagonal stresses. One diagonal tension, the other diagonal compression. So this diagonal will be in tension and this diagonal will be in compression due to the shear stresses. And in order to establish what is the magnitude of force that is experienced, magnitude of stress therefore experienced by the diagonal, we will consider an element in 3 dimensions. And let us assume, for the sake of simplicity of our derivation, let us assume this to be 1, that is unity, this dimension to be unity, and this dimension is B. So this particular rectangular element, say rectangular element, has B and B. It has a square face, B into B, and this is the surface which is subjected to shear, and this is yet another surface, and here is the diagonal surface which is shown in dotted lines, and the thickness is unit thickness. Total force on the face AB, here AB is the stress into area. Stress is tau and area is B into 1. Therefore, it is tau into B into 1. And this same force is experienced by this particular surface denoted by AB and this particular surface denoted by BC. And resultant on the diagonal AC will be simply square root of and if we plot this particular force to scale, and this will become horizontal and this will become vertical, and the other force will be definitely along the diagonal. Therefore, the length can be taken as the force. Therefore, it is a square root of tau b square using Pythagoras theorem, of course, or law of triangular forces. Tau b square plus tau b square, it becomes, upon simplification, root 2 tau b. This is the force acting on this particular diagonal surface of unit width. Length of the diagonal happens to be, this is B and this is B. So square root of B square and B square, and we will get root 2B. Therefore, we can calculate normal stress on BD or AC. BD is a diagonal, AC is a diagonal. It is a total force acting on the diagonal surface divided by area. So it has been proved that the force is root 2 tau b and root 2b. Root 2 will cancel, BB will cancel, and we will just get tau. So the meaning of this particular expression is the magnitude of diagonal tension and diagonal compression is the shear stress which is acting all around. So this is a very interesting observation that we are making, that if shear stresses act on the complementarily over the element, the diagonals will be subjected to tensile force or compressive force, or tensile stress or compressive stress, one diagonal. And interestingly, the magnitude of this tensile stress and the compressive stress in both the diagonals will be tau, the shear stress that is acting. And it is a very important case because the shear, the external force, external stress is shear, but the internal normal stress is once again shear in different form, of course. Relationship between E and G and K. Now we can conveniently proceed with our goal of this particular tutorial. And here is the square element. This angle is 45 degrees, and this is one of the diagonals. This is other diagonal, and it is subjected to all round shear. Now it is subjected to this kind of an effect. A will move to A dash, looking into this particular sense of this shear stress, and B will move to B dash, and this is the shear stress tan gamma is the shear stress. Therefore, if we and we will connect this particular point, dislocated point A dash and C for the derivation. For the sake of derivation, we will also draw a perpendicular from A which will meet this particular red line, that is the diagonal, extended diagonal or stretched diagonal at E. And therefore shear strain, which is tan gamma, equal to AA dash, that is opposite, by AD, that is adjacent. So since the gamma, the angular deformation is too small, very small, then tan gamma will tend to become gamma. Therefore gamma is AA dash by AD. Now the angle AA dash E can be assumed, can be regarded still to be 45 degree because AA dash is very small. So we make this compelling assumption in order to ease out our derivation. And if this angle is 45 degree, since this deviation, since this dislocation or this deformity AA dash is very small, therefore we are not erring if we assume that AA dash E is still 45 degree. And we will take see the angle AA dash C can still be considered as 45 degree because of small deformation, that is AA dash. And we will in the triangle AA dash E, and this still we are arguing that this is 45 degree, still 45 degree. Therefore this angle is still 45 degree. Yeah, and we will just want to replace this AA dash by some other notation or some other variable, some other element. Okay, in triangle AA dash E, cos 45 degree equal to adjacent by hypotenuse. Adjacent is A dash E and hypotenuse is AA dash. Then we have a replacement for this AA dash over here, and AA dash happens to be A dash E divided by cos 45 by just tweaking this particular equation. So A dash E divided by cos 45, because we need to replace this AA dash over here. So continuing further, so we have gamma now, A dash E divided by AD cos 45. In the triangle ADC, we will go back to see what this ADC is. This is ADC. This angle is 45, and if you take cos 45 again over here, we will find AD cos 45 equal to AD divided by AC, the adjacent divided by hypotenuse. Therefore we will be able to remove even A dash E also. So AD also. In the triangle ADC, cos 45 is AD divided by AC. Therefore we can find a replacement for this AD. So what we find is, so that AD equal to AC cos 45, therefore gamma over here is no longer this particular expression. It is A dash E divided by AC cos 45 into cos 45. Cos 45 is 1 by root 2. That root 2 into root 2 will become 2. It will go up. It will go up. It will find its place in the numerator. And what we find is gamma equal to 2 times A dash E divided by AC. A dash E, if you watch carefully, A dash E is nothing but the change in length of this diagonal, and you can always assume CE equal to AC. I repeat, we can always assume AC equal to CE. So after assuming this AC equal to EC, for the simple reason that AA dash is too small, we are also arguing that A dash E is the elongated length of the diagonal. Okay, elongated length of the diagonal, that is change in length of the diagonal. Yeah, A dash E, and it is 2 A dash E by AC. A dash E is the change in diagonal length, while AC is the original length of the diagonal. Therefore gamma becomes 2 times epsilon. This is change in length of the diagonal and divided by the original length of the diagonal. Therefore gamma, we proved shear strain equal to twice the linear strain. This is also a very important observation which should remain with us as a fundamental. So therefore this is a pointer for us to understand gamma is always severe. because it is twice the linear strain. This indicates that the shear strain is twice the longitudinal strain. This is a very important observation, my esteemed viewers. And so we are here. We will once again continue our journey for obtaining the relationship between E, G and K. So this is number one, a very significant observation. Continuing further, from Hooke's law, shear stress is proportional to shear strain. And if we remove this proportionality symbol, we will get G. And G is a measure, is a modulus of rigidity. And gamma equal to tau by G. Gamma equal to tau by G, a little adjustment in this formula. Therefore, tau by G equal to 2 epsilon. That we have already proved. So, gamma equal to tau by G. And gamma is already been proved as 2 times the linear strain. Therefore, tau by G equal to 2 times epsilon. Therefore, we are bringing in relationship between shear stress, rigidity modulus and linear strain. So this happens to be another significant equation. It has been just proved that all round shear stress over an element, one diagonal will be in tension and the other diagonal will be in compression. In both diagonals, the magnitude of stress is tau. And if we sketch it simply, this is the diagonal which is undergoing tension, and the tensile force or tensile stress in it is tau, and there is a shear stress, there is a longitudinal stress, there is an axial stress which is pressing this diagonal, and this stress comes from the compression of the other diagonal which is orthogonal to this. Therefore, this tau as an axial stress in one of the diagonals is contributing for the increase in the length of this particular diagonal. Therefore, if we calculate the net strain along this particular diagonal, the net strain along AC, let us say, therefore net strain along the diagonal AC equal to the primary strain that is happening over the diagonal exclusively due to tau and the side effect. It is positive because this is also contributing for the increase in the length of AC. Therefore, tau by E plus mu times tau by E. This is exclusively due to the tau acting perpendicularly all over the length of this particular diagonal. Therefore, the net strain experienced by diagonal AC is the primary strain due to axial stress in the diagonal plus the secondary strain or the side effect or the Poisson's effect. Therefore, placing equation number 3 in 2, that is, here we have said like this. Therefore, I will just move this expression over here. Therefore, tau by G will becomes 2 times this particular expression. Yeah, tau by G equal to 2 times tau by E into 1 plus mu. Tau will get cancelled and E will be cross multiplied. E will go over here, G will move over here, and we will get a very important expression, very first expression which relates E and G. So now we should remember forever that elastic modulus is related to G linearly. So E equal to 2G plus into 1 plus mu. Equation 4 relates E and G. Continuing further, we discussed in our previous tutorial that bulk modulus is given by K equal to sigma V volumetric stress by volumetric strain. Of course, there is no concept of volumetric stress. This volumetric stress is coming to be called as spherical stress. It can be connoted as sigma V if and only if sigma x equal to sigma y equal to sigma z. This equation our respected viewers can kindly recall, or they can go through once again the previous tutorial, that is tutorial number 8. And there we have proved volumetric strain is given by 3 times spherical stress. 3 times volumetric stress divided by E into 1 minus 2 mu. Therefore, we will just write the expression over here by moving this entire expression in the place of epsilon V, that is volumetric strain. So sigma V will get cancelled, E will go to the top numerator, and E, when you equate E with K, this is the expression. This equation relates E and K. So we have got 2 relationships among 2 variables. in a sequence E and G and E and K. So E is related to K like this. And in both the equations, one thing in common that should be observed in both the equation is the participation of the Poisson's effect in terms of a ratio, that is mu and mu over here. Therefore E is related to K by means of this particular equation. Therefore this is the fourth equation and this is the fifth equation. We will further continue using this equation, that is E equal to 2G plus 1 plus mu, which is equation number 4, and we can write for mu. So mu will be equal to E minus 2G, and if you E minus 2G, 2G will go that side, divided by mu into 2G it will be, and we want mu, therefore it is E minus 2G divided by 2G. So we have an expression for mu in terms of only moduli of elasticity E as well as G. So we substitute expression for mu in this particular expression because we need to involve with K also. Therefore we chose the fifth equation, E equal to 3K into 1 minus 2 mu, and this mu is substituted over here. Therefore E becomes 3K into 2 times mu, 2 times mu. In the place of mu we are going to place this over here, it is minus, okay. Therefore it is 2G is already there, okay, and we will get this particular kind of expression, 2 times E minus 4 times G divided by 2G. Okay, and when you take LCM, 2G will come over here, 2G minus 2E plus 4G divided by 2G, and 4G plus 2G makes it 6G, 6G minus 2E, and we will take 2 as common factor, 2 and 2 will get cancelled away, and we will remain with 3G minus E. So E equal to 3K into 3G minus E divided by G. Now, therefore, and upon further simplification, GE, when we cross multiply, it will equal to 9 kg minus 3 ke, and we will just group the terms containing E, and we will take E as the common factor, so it becomes GE plus 3 ke equal to 9 kg. Therefore, I repeat, GE plus 3 ke, it goes this side, and we will take E as the common factor, and we will be left with 3K plus G as the factor. And since we want an expression for E aloof, and we will find this expression upon simplification. So E equal to 9 kg divided by 3K plus G. This is one of the significant derivations that we do in strength of materials. It is significant because it relates 3 different properties of materials, of course within elastic limit. One is K, the other one is G, other one is E. Therefore, in this tutorial, we have to remember we have established 3 equations. E equal to 2G into 1 plus mu relating E and G, and E equal to 3K into 1 minus 2 mu relating E and K. And we have developed another relation like relating 3 variables, 3 important modulus of elasticity, that is E equal to 9 kg divided by 3K plus G. My esteemed viewers, with this we are closing this particular session, this particular tutorial session, which essentially brought to the fore the relationship between E, K and G. And until I come out with the next module in the increasing order of proficiency. Until then, it is bye, and if you have liked this video, kindly subscribe to my channel. Thank you.